channel dot diversity. Here we will be bandwidth that person the channels in the and bit loss, diversity, selection and outage probability, character performance. And so here we will start by the mathematical example with the best step solution. FC, then the bandwidth and time is how far time, whereas WC by TC quantifies how frequencies. So the rough rule is that fading when bandwidth is and the frequency predictive when it is greater than omega. Right? It is like since you have bandwidth as B, the process that range. That case, the signal will be so for example, you have FD, which is a common heuristic. XTC is equal to 1 upon 2 FD, derived last week. And for the delay spread of T of RMS, the rule of thumb is definitely delta C is equal to 5 into T. For example, if you have 2 seconds, and that is the working example for 5G, and WC equals to 100 kilohertz, and 16 COM modulation at RB is equals to 1 Mbps. The rate will be given as, since it is 16 COM, RC is RB divided log 2 of M, or here M is 16, log 2, 16 to power 6. It is actually 6, RB by 6. And with L by 3, and once feeding in time, which is here, if you calculate bandwidth is greater than it is, the options are you can select frequency select. How you have to fast feeding, add versus frequency select. And there's also a term called time selective. Then the top time selective Doppler spread. And when or both are moving, at least really channel it coherence time. And if us is there, channel varies significant is a similar here. That if all It is discussed on the particular symptom. But in we are having suppose it discusses that case it will talk about math and selective index measure. Sequence selective it was C divided by omega. In versus past you have mutate x which is f is equal to WC interval of this interval and it is and are also talk the Doppler spread in the same time, but he was like particularly always remember try to find where the DC this is nothing. There above example bandwidth is good. Whether it is lift, whether it is frequency selective, whether it is flat fading. Calculate it. And in that case, you have to take with respect calculated here for Annu is very greater than one. Not very greater than, but it is significantly than one. So in that case, and greater than so it is practically the bandwidth and in that case all about that fading. Now I will move to reference limit. That interference limit test where you're having a high interference. Interference the objects and noise of any company that induces a thermal noise. It can often be higher happening that part of reflectors, part of multipath. I asked you like at what times basically the signal quality degrades by more than 3 dB. So it is lambda by 2. That's why all the antennas are designed in proportional to lambda by 2. Because if we the frequency, that degradation is happening at every distance, and that can be as small as 30 centimeters. So if we have seen in childhood that a scale that was 15 lambda is equal to 30 at the distance, your signal will degrade just by half. So that will fall in by I plus N. Then we are having high interference and the input targets interference deviation more than. So if I is very greater than N, that case N is greater than C by I, and in that case it is not equal to I. So one of the working example which I have created for you is like suppose you're having C by N is greater than C by I, and in that case if it is I is greater than N. So another option was given in the last year previous assignment by N plus I, which is equals to and it is a very, very false interference limited case. So there was one tree, and here you were having so many objects. If you have one object two, here the interference is happening from three. And if I talk about even case, noise is associated with this inherent property of any electronic device will be from one receiver, one transmitter. So here in this case, I is very, very greater than N. There's one scientist who the concept of Doppler spectrum. So the scientist name takes time, takes this Doppler spectrum. Here what happens when we have isotropic scattering. What do you mean by isotropic? The scattering is happening in all direction, and in that direction it means. And here in 2D, we're having the object with respect to x and y. The Doppler power spectral density actually it will be U-shaped. The port of capital mod of f is less than equals to fd, which implies f ranges from minus f plus f. So if you say the mod spectra, so in passing through calculate the power spectral density, that case is coming by ft minus f by ft mod of ft is equals to. So if I just plot here, one upon first for you is at 0 power at 0 previous power equals to after full. So if you have example, if FD is equal to 100 hertz, you have to evaluate RH of tau at tau is equal to by FD. Tau is equal to 5 in 0.5 into 10 power minus equals to 5 by RH of 2.5 milliseconds. And if you keep the Jake's formula coming 0.2. Okay, so we will be the next topic, line of sight and sight Doppler. So concept is like we have line of sight, which introduces a discrete delay Doppler rule at f is equals to md cos theta, which is a discriminated power. It's superimposed on a diffuse component of different scatters. So pure non-line of sight tends to follow a zero power spectral density. So if we talk about a simple formula, so it is equals to h s of x h LO s of f, which equals to p naught delta f minus f naught. That's s equal to f, where f naught is equals to fd cos theta naught. Why here the f naught is equals to fd cos theta naught? Because it is through the Doppler, and we know it is how the frequency will change with respect to Doppler frequency. So work example is a spectrum showing a power spike and f is equals to f. over Jake's like base indicates line of sight. If f naught is equals to 80 hertz, with ft is equals to 100 hertz, the angle of arrival which follows cos theta naught is equals to 0.8. So what will the theta naught? So here the vehicle or any user is moving with respect to the constant base station. This theta naught is equals to 36.9 at the angle of 37 degree. It is B, and the spectrum will have the spike as f naught. Now we will move to the topic of maximum Doppler shift and the coherence time. So the concept is Fd, the Doppler frequency is equals to d by lambda. What is b here? B is the velocity with which the vehicle is moving. So is equals to vfc divided by c. Why here? Because I am replacing lambda with respect to fc by c. So what does it represent? So it actually represents the highest speed and the carrier causes larger FD, thus a smaller TC and a faster gradient. There are some formula based analysis like the TC is equals to 0.4 by FD, which is equivalent to 1 upon 2 FD. So if I give you the worked example, FC is equals to 3.5 gigahertz, V is equals to 30 meter per second, then FD is equals to 30, directly putting in the formula, 30 3.5 into 10 to the power 9, because here 3.5 gigahertz divided by C, which is equals to 3 into 10 to the power 8, and you are getting MDS 3 hertz. So just imagine the values. Like here you are having the Doppler frequency of 350 hertz, but a center frequency of 3.5 gigahertz. So it is differentiating with respect to 350 hertz. The coherence time is 1 upon 2 FT, and which is equals to 1.4. That is a coherence time. So the next concept is autocorrelation and level crossing. So as we know, time selectivity shows up our edge of tau, and in second order metrics like level crossing rate and average fading duration, which is AFT, for relay fading, which is for the non scenario with average power of LCR at threshold is NP by root of by FT. AFT is, please try to remember this directly count. You have FT is 100 hertz. Threshold is equals to 0.5, which is rho. Then you have to calculate this, and finally the average fade duration, like time with which fade will last, that is AFT, and in that case, it's 0.3 milliseconds. Imagine with the Doppler frequency of 100 hertz, you're getting average phase duration as every 100 hertz, they're getting 2.3. So just if you're at the velocity for a certain limit where the FT is also increasing because FT is directly proportional, in that case, the average phase duration that will last till 1 second. So imagine your signal will degrade up to 1 second and you'll not get any signal connectivity if that is the case. Now the next one is time frequency duality, like which is ISI and ICI. So the concept is time selectivity. This TC, this ICI in OFDM, this spread on WC, this ISI is involved. So inter carrier interference, the signal interference is a difference. ISI in single carrier and subcarrier selectivity in OFDM. And we are having a different multi-C induces the IC. And if you have a single carrier, in that case, subcarrier selectivity will be happening in OFDM ICI power is directly proportional to FD into TS square, FD into TS. Cyclic prefix needed if the T of max delay is less than T of CP to avoid ISI, and T of S is equals to 71 microseconds, so 14 subcarrier OFDM twice a day. Let's say you're having 14 subcarrier, FT is equals to 200 hertz. In that case, FT into TS is equal to 0.01, and which is very, very negligible as compared to ICI. And if the delay spread tau of max is equals to 4 microseconds and T of CP is equals to 3 microseconds, ISI will occur. Cyclic prefix will be very, very small. What is the average length for cyclic prefix? So it is 1 by 16 into simple time. And that will last till 3 microseconds. Okay, so we will move to the next topic, which is sum of sinusoids, the Jake's model. So the concept is we have to simulate the Rayleigh fading by summing complex sinusoids with appropriate chosen Doppler shifted frequency and phases to match this autocorrelation function, which is a function of tau and power spectral density. So what is a Rayleigh fading? So that we can write as a sum of sine and cosine. And here the constant term a and b, which is equal to by n. Here, why we can write the Rayleigh fading as sum of complex sinusoid? So as per Fourier series, if any periodic signal is there in time domain, that we can write as sum of sinus and cosine. Okay, that is the concept. So HT is equals to root over 2 by n summing cos 2 by f t plus phi n plus j root of capital N 9 2 by f n t plus, here the phases are different. You can see this one example. Ft is n is equals to n on, and on here choice is fn is equals to ft plus 2 pi n by 4, then n is equal, here n is integer, that too positive integer. What is that? It is a natural number. You cannot assume a negative. Why you cannot assume a negative? Because cos negative of x is actually cos of x. Because cos follows symmetricity with respect to x. Is the uh, graph for that? It is. We talked about this a lot in previous classes because cos is actually an even function. An even function has property as x of equals to x of t. Odd function has property of x of minus t, x of minus t, minus x of minus t, and it is having symmetricity with respect to origin. That is the difference. Now, if I ask you which oscillator frequencies are valid, you have to check the natural number, and if any option sets outside this particular interval, then it is obviously that is not an oscillator frequency. So for example, values like 100, 99.55, 99.8, If all aligns with n is equals to 1, 2, 3, value like 99.62, that may not match for any n for the choosing capital N that varies it. So in that case, you have to pick that option and keep that value. Now, if I ask you about FFT and IF, what is that? So in that case, we have to generate a time series to target a power spectral density by shaping a white noise. What you have to do, you have to first keep the root square of power spectral density and then apply IFT. So here IFT not to convert from frequency domain to time domain. It is very similar to TFT. The only difference is here you are having the butterfly structure which helps in the computation. So suppose steps are like you have to first generate the IID, complex Gaussian, have to filter with respect to A is equals to root over power spectral density at every FK multiplied by W and then finally H n is equals to here H of F where it is in time domain equals IFT of capital H of K which is duration by n of K. So I have given you one example you can look into. Here you have to choose principal as Fk and then IFT to obtain H of n of duration of n ts is equals to 5 seconds. So I'm skipping some of the examples I have created, but I will share this PDF to all of you. Second concept comes like maximum ratio combined. So what is that? If we are having input transmitted as X, so you're having different spectra at different parts. The receiver is let's say Y1. And you want to combine it again Y1, Y2, W1, Y1 plus W2, Y2. That is completely Y. Let's say if I'm writing the form vector, so Y bar is equal to W bar trans Y dash of that. So maximum, as the name suggests, maximum. You have to maximize it with respect to the received signal strength indicator or maybe some SNR. So what exactly I'm getting is W should be proportional to H. What is H? H is a fading vector. And magnitude of H is actually Rayleigh fading. And phase of H is uniform distribution. So 1 upon minus A square divided by 2A cos the Rayleigh fading. And phi of that is what upon 2. And once we come the exponential distribution, then we get as a gamma distribution, which is basically for all the MRC. Because exponential is what here? This Rayleigh fading. When you sum all the Rayleigh fading channels, then you are getting the gamma distribution. And the gamma distribution are in this form. And also, if you're asked to calculate the outage probability, then it is 1 minus around 0. bring this topic of equal again. I would like to derive the expression expected gamma distribution. Like if you are having IID delay branches, you have to use the of mod of S to derive the mean. Here the math, like the magnitude of fading component is really distributed with respect to sigma, and the expected value is equal. Then we are having mean square value, which is equal. This here sigma square was there in the denominator, equals to 1 upon a squared. Here that's why it is equal to is equal to of sigma square. And since we need to match with respect to power of 1, as we need to normalize it, then 2 of sigma square is equal to 1. And simply the expected value of summation of I is equals to 1 to m out of hi square is generating from C of h square plus m mc2 factorial of m plus 2 of m mu m array. Number scale briefly using question with really distribution. As we know, probability of DP is and if we keep 10 cancel. This is one of the outage probability example. And if we keep m is equals to 4, y is 3 dB, and we are getting 0 107. Like exactly, it's very less as compared to the one which you got later. In practice, the outage probability definition is like the outage will occur when the instantaneous SNR falls below the threshold required by NCS quality of service. So it is actually when the the SNR is less than the threshold SNR, and the relay single branch P of out is equals to nothing but 1 minus e power minus gamma TS divided by gamma with SC is equals to 1 minus e power minus gamma TS divided by gamma power M. With MRC, you complete gamma CDF. So if we have M is equals to 2, gamma TS is equals to P of gamma. That case, P out of SC is equals to 1 minus e power minus 3 divided whole square is equals to 86. Now the question arises, how can we select the threshold from the target PER? For a target PER, we have to map to a SNR threshold via AWG and apply appropriate failing margin. And if we have BPS AWG and equals to of root of SNR, we have to calculate power TH. And if we have worked example for 5 Q of 4.5 gamma capacity in fading with and without diversity. Diversity reduces rate because here we are having more mix. So increasing E of log 2 SNR with the water filling up branches and subcarriers further improves the capacity. So C is equals to E of log 2 1 plus SNR MRC. MIID exponentials where gamma is directly gamma distribution to computed via integration or quadrature. So if we compare M is equals to 1 and gamma is equals to 5 to C per hertz and mod. The interference limited outage. For example, we have concept as replacing noise N by a random interference I may be approximated stable thresholding and we will have when it's with a single dominant the relay faded probability of SNR is with a single gamma I divided gamma. How we will compare this SC with respect to MRC always means the outage probability of for example this 5 let's say both are 5 calculated 0.39. What do you observe? Like for MRC, which is I talk, like to calculate the diversity, give a reduction of out gamma bar. We are always talking 10 power things, 10 log 10 terms of square. That square cancels divided by 2, x divided just the values here. And there were no questions related to that. Questions were related to frequency. Have clearly covered those, fully covered those. Takes frequency parity when there you have to if it is a function, then the values values such that it satisfy fn is equal to ft cos 2 pi n divided by capital 4. And what is ft? Ft is very, very less. Value frequency 5.9 ft was 150 hertz. And with every 100 hertz, you will get the spread of when we get the ft 1000, the spread will be multiplied 23. Just see, suppose we are having a vehicle heading at the angle of arrival is the not is equal to 50 hertz. Ft is definitely it is 2.3. Where is the lowest where you will get this line of sight center frequency. Basically, the center frequency will let's see. So F naught is ft for lowest, that is equal to 3 degrees. So for that's the frequency of 5 hertz, you will be getting this. If they have already have some IT standardized multipath fading urban suburb, which is widely used for channel impulse response alpha I delta T characterized by multipath fading. But here it is HT. So far we talked about H. N of T, right? But when we talk about wireless channel, wired channel, H of T, just a summary. First feeding coefficient, and actually this part is channel impulse. There were some concepts I have done the similar pattern curve. going to start and next reducing the exponent. Then you will be getting the expiry delay will be correlation function approximates SL0 and the limited number periodicity correlation. So 1 hour is about to over, and what we have talked about is like we have to classify channels, the Doppler spectra, getting the fading via James, SCMRC, EGC metrics, evaluating the outage, reason about implementation and trade-offs. The next part is like we have to extend it to MIMO, frequency selective fading, and the interference formulation. Okay, so I'm taking 5 minutes break. In journal, we have fading types like bifurcated in two parts, large scale fading. Large scale fading has path loss and shadowing from multipath Doppler spread. Multipath delay spread is again having two parts, flat fading, frequency selective. Doppler spread is having two part fast fading and slow fading. Even this conditions like when BS is less than BC, BS is second bandwidth, BC. Frequency selective fading, we are having the BS is greater than BC. And fast fading, when we have time simple, be better than this coherence time, and that is the case for fast fading when we have TC is greater than TS, very greater than TS. That case, you have that you can at least take a screenshot or I'll upload this topic. podcast we discussed about diversity. Today we are talking technology. Here we are having a diversity is actually liability. MIMO cannot direct possible by transmitting several information multi transmit model from MIMO information and we trans sometimes we are having three R dimensional by of R cross one. First one because the blue of R cross D. H is equal to H1 H1 H2 H range is HRM H of IJ is eight cup channel coefficient IH is of channel coefficient R into T is and R is equal to cross 2 dimensional by 1 by T is equal to W we are having single and fading channel coefficient. WI is the value of WI into the WI. Otherwise, and I is and sigma square around 9. The sigma engineering IID noise MIMO receive by bar is equals to how to recover X bar and bar is equals to H is equal to R cross M matrix. In that case, receiver is like when R is greater than tall matrix. In that case, you are having multiple solutions. Number of receiver antennas you're having R equations, yeah, for determine system. For equation greater than number and number of equations greater than number of unknown. In that case, we are having either no big solution is. So suppose we are having I x1. We are having two equations, three equations plus two unknowns. Either the solution will exist, otherwise it won't exist. The unique solution or no solution. But it is overdetermined. Overdetermined. So in that case, the approximated. If the solution exists, it's fine. But if no solution exists, we'll approximate. And in order to approximate, we get the solution which has the least error. So in order to minimize the error, we have to find x such that mod of y is less than h of x bar. Minimize least bar. Find we have to define 0 over x bar is a vector. Transmit vector derivative. So del f of del x is del f for del x1, del x2. del f of del f. Derivative of f with respect to every element x. So if we this determines the three equations but less number of either solution, otherwise no solution. That is equals it is zero for single x is complex and it x right MIMO 0 for single and it is a inverse of left inverse of h and h identity calculate left inverse. Right, what is right inverse? Left inverse is it is multiplying, it is giving here. Right inverse, like if it is multiplying here, it is giving here. And it is A into A trans. It's trans A into cover this topic. Thanks. calculate the bit error rate of consider a matrix H with all element identity complex establish power of 1 and transmit power nothing but P. The expected value of xi squared is equals to P in that case. The ER for BPSK with 0 for C fever, nothing but an MRC system. In that case, with L is equals to R minus T plus 1. And from the previous formula derived, we can take directly at higher SNR, which is equals to 2L minus 1 CL 1 by 2 SNR power L. So with L is equals to R minus T plus 1, we can consider L minus 1 L 1 by 2 SNR per L. That case, have T cross 2 minus 20. Why this is like this? Because here it is acting as MRC L R and antennas. So N is equal to R minus T cross MO system R is equal to IDV. So force there. What is the average BR? This case L 1 by SNR power L. That is will be 3 by 4 error rate. 5 it can X is equal. It's similar to MRC, like I have a similar X bar. H1 hence that is directly for H and achieve a state challenging and position up to the this year the when we are here L minus L is R minus nine does not because SMR transmit H bar transpose of does not need very powerful as we know first really can letting her do back of okay, thank you so much. Me by email, YouTube channel.